What if paleontologists could create robot replicas of dinosaurs to better understand them and how they moved, and in turn, learn more about us? Hello, you're listening to where What If becomes What's Next from Carnegie Mellon University, where we explore what AI means to industries, government, society, and you. On today's episode, we're talking about the intersection of paleontology, robotics, and artificial intelligence. That includes paleobionics, an emerging field at CMU that uses robotics and soft robotics to help scientists better understand how dinosaurs and other extinct organisms might have moved based on their skeletal structure. Not only could this lead to new discoveries about dinosaur behavior and evolution, it also could provide new understandings on how we, as humans, move, while helping engineers design more agile robots that move better through our world. And that's something scientists can't get from fossils, bones, and dinosaur tracks alone. This kind of technology excites paleontologists like Dr. Asia Mia Carter.
Why, as a paleontologist, I came into robotics is because I want to see and understand my animals as if they were alive again.
Asia is a postdoctoral researcher working with CMU's Robomechanics Lab, and she's using robots to bring some of her favorite prehistoric animals and dinosaurs back to life.
I have worked on dinosaur fossils, including one that's in Jurassic World, which is like a really huge achievement for me. But now I work on robots, and you'd think that's strange, but it's more connected than one might think.
Asia, explain to me how you see this interconnectedness between paleontology and robots.
So a big part of my work is using the fossil record to inspire new designs, to think about how these ancient designs might be more suited for tasks that we want in our robots. And in turn, the robots help me learn a lot about ancient animals. One of my favorite questions, which will take my career to answer, is what was the very first animal to run? That's a really hard question to answer, right? We have an idea of some of the first flyers. We have an idea of, some of our earliest terrestrial animals, ones that are walking around. But running? That's a dynamical gait, right? And if you want to have good models of dynamical behaviors, you need a good robot. So that's how paleontology can help robot design, and robots can help us to understand paleontology.
How is this emergent field of paleobionics giving new insights into prehistoric, as you call them, critters, and life in general?
When we use robots to understand extinct animals, we're not just learning more about a dinosaur or an ancient amphibian. We're also starting to understand the rules of life, right? So the way I think about this is it doesn't really matter if you're an elephant or a dreadnoughtus, the sauropod that I helped work on, or some salamander.
I want to jump in quickly and say that scientists discovered the dreadnoughtus more than 10 years ago. It's 85 feet long and weighs around 65 tons, making it the largest animal to ever walk the Earth, at least that we know of. Okay, thanks, Asia. Please continue.
Gravity is gravity, and there are some hard limits to moving around in the world. What can we learn about those hard limits, those fundamental rules, by exploring the fossil record? And the way we learn about mobility in extinct animals also tells us about ecology. So predator-prey interactions, establishment of terrestrial ecosystems, a lot of that is linked to what you can run away from and what you can chase. So learning more about the behavioral capabilities of extinct animals tells us more about how ecosystems evolve through time, what future ecosystems might look like, this really big holistic approach to both underlying mechanics of moving through the world and the evolution of terrestrial ecosystems, particularly in my work. When we were working on Dreadnoughtus, it was very old school, very classic, very, 19th century techniques, 3D scans, which were new at the time, but are now very old. We had an amazing understanding of the skeleton, but skeleton isn't behavior. And that's really what we want. Robots, in some cases, have helped us to understand potential gaits. By creating robots and then simulating how the animals might have moved, we are getting understanding of what gaits might have been like in these extinct animals, which is really exciting.
How does this translate to designing better robots?
It's not just understanding extinct animals and a steady state behavior. I know the animal walked. Tons of things walk. We know that. but they're in an environment that has mud and grass and fallen trees. How did the animal navigate that? We need robots to be really mobile and dexterous in their environment. And I think with some of this work, understanding how design changes affect mobility, maneuverability, and capability in different environments, we can build robots more suited to their task and their environment, like having them assist humans. So again, it comes back to understanding really deeply this baseline understanding of environment and task and design, and then how we might turn all those knobs for when we do want to send our robots closer to interact with humans.
What organisms are you studying right now in the robomechanics lab?
We are exploring the behavioral capabilities of an animal called a gorgonopsid. It is a strange, not quite mammal, not quite reptile. It's one of our ancestors, and it was one of the predators in its time. And it has a very strange, at least to us now, morphology, where its forelimbs are more sprawled, think like crocodile or its salamander, and its hind limbs are semi-erect. There's nothing like that anymore, right? All animals are either both sprawled or both erect. And we're really interested in understanding how that kind of design change might change the capabilities in our robots.
How are AI and robotics changing the way paleontologists are analyzing fossils or tracks, or going back and looking at the ecosystems of extinct species?
One of the techniques we use in paleontology is called geometric morphometrics. And that says, well, how different is the bone, right? If you look at my shoulder and you look at a cat's shoulder, there's some similarities, but they're different. Normally, we have to put those points on ourselves as human beings. But if you want to do these big data studies and get a lot of information, use a neural net. So while I use robots to do locomotion, neural nets and AI are starting to come into the anatomy part of paleontology, and that's going to give us access to way more data. And with way more data and big data sets, we can ask questions in ways that were not possible before.
I was reading about how artificial neural networks work similar to the human brain and how they analyze and learn from information. Of course, they can process larger quantities of data and do it faster than humans. What's an example of how AI tools like neural nets are helping paleontologists answer questions that seemed unanswerable before?
One of the questions really prevailing in paleontology is what is the difference between a trait that becomes a novelty, so only one or two animals will have it, and something that becomes, de novo, every animal has it. And with these really big data sets that we can now analyze with AI, we might be able to start teasing more of that information apart, which in turn helps us get back to robotics and design to say, okay, well, this trait, you're going to become a specialist. And maybe you only want your robot in particular areas or doing particular things. But if you want, a general kind of Swiss Army knife, a general robot, maybe take this trait instead.
What's a burning question you hope advancements in AI and robotics can help answer?
I think one of the big ahas is going to be figuring out which animal was the very first animal to run. Because let's think about this for a second. So we were first kind of fishy, and then we were a little less fishy, and now we're kind of salamandery, and we make the transition to land. Either the second we touch down on land, we are also able to run. And that's really interesting, that the transition, you just have all the parts you need to go do novel behaviors that have never been done before in the history of the planet. Or it takes some time. Is it not for 20 million years that we're able to run on land? Is it not till almost the age of the dinosaurs, which is almost, 100 million years later? Because if we do identify the first runners, the first animals capable of this energetically expensive dynamic behavior, what environment were they doing it in? If my hypothesis is correct and check back in a few years, I'll let you know. If our first runners were the animals I'm thinking of, then we evolved to run in sand. I don't know if you've seen a robot try to navigate sand, but it is really challenging. And then something that I'm excited about, right, is if we can think about all of this locomotion and all the evolution of these behaviors, can we design better systems for space? If we were ever going to send a legged robot up to the moon or somewhere like that, can we use this information to build designs and environments we can't imagine right now?
Looking way back to help us look forward. Thank you, Asia. Let's take a quick break. When we come back, we'll get insights into the origin story of Paleobionics at CMU. And can scientists someday recreate a robotic life-size dinosaur? We'll find out next from our guests on where What If becomes what's next from Carnegie Mellon University.
Hi, I'm Steph Strickland, and I'm your host for Does Compute, the podcast where we delve into the latest innovations in computer science with the help from experts at Carnegie Mellon University School of Computer Science. Join us as we explore the real-world impacts that computer science is having on our lives and our future. We'll look at AI's challenges and opportunities, how new research is influencing fields like healthcare and education, technology and the environment, and much more. Whether you're a tech enthusiast or just curious about how computer science is building useful stuff that works, tune in as we hear from some of the brightest minds in the field and uncover remarkable ways that CS is shaping our world. Listen to Does Compute from CMU and GeekWire Studios. You can learn more at www.geekwire.com/doescompute.
Welcome back. You're listening to where What If becomes What's Next from Carnegie Mellon University. Today we're talking about paleobionics. It's an emergent field at CMU that uses robots to deepen our understanding of how extinct prehistoric organisms move through the world, answering big paleontological questions. It's also helping scientists engineer better robots. For example, researchers from CMU's Department of Mechanical Engineering worked with paleontologists to develop a robot recreation of an ancient marine organism called pleurocystid. Paleontologists have long been interested in the pleurocystid because of its critical role in the evolution of the present-day starfish and sea urchin. The CMU researchers designed their robotic version based on a 450 million-year-old fossil. The robot looks like a small stingray with a hard robotic body and soft robotic appendages. Without soft robotic technology, this swimming, crawling robot couldn't have been built. CMU mechanical engineering professor Carmel Majidi was one of the leads on this project. Carmel, how are you bringing soft robotics and bio-inspired engineering, looking to nature to inform design, into paleontology?
I've always actually been interested, as long as I've been doing research within bio-inspired robotics, to work with folks in this evolutionary biology domain and really understand, like, why does an organism behave and function the way it does? So that's always been a big question for us within the field. And then soft robotics, we can almost bring things full circle because these are now test beds where we can just build pretty much anything. So why limit ourselves to replicating organisms that exist today?
How did you land on the pleurocystid for this work?
We were actually building a robot starfish, and we realized that the starfish is, and brittle stars are a very diverse organism. And to really understand that, we had to kind of go back to see, okay, well, how did these organisms evolve? And then in talking with the paleontologists who specialize in doing research on pleurocystids, we realized that, wow, these are actually really important organisms. Among the first marine organisms capable of locomotion using a muscular stem. So up until that point, organisms, they would just float around, or they were just kind of like flat, but they couldn't like push themselves using a limb the way that we and most other modern organisms do. Since then, we've had a chance to meet on a few occasions with paleontologists here at the Carnegie Museum of Natural History and learn about other organisms that also occupy important points in evolution, and especially when it comes to introducing new ways of locomotion. And so we realized that there's actually a really kind of rich body of opportunities to kind of apply our soft robotics manufacturing methods and designs to kind of resurrecting quite a number of different types of extinct organisms.
What are you basing your recreations off of? Is it only the fossil record?
With a lot of these organisms, all we have is the fossil record, right? We don't and we don't have necessarily modern day analogs to these organisms, and so it's a mystery. So by creating these synthetic soft robotic versions of them, we can actually perform all sorts of tests in all sorts of different conditions to test out the different hypotheses that paleontologists have had about how these organisms moved. And then as we learn about that, that really helps us unlock just fundamental principles of locomotion in general that not just are important within natural organisms, but that can also translate to building better robots.
I think this is a good segue to my next guest. Aaron Johnson is an associate professor of mechanical engineering and robotics at CMU. He's also faculty for the university's Robomechanics lab. Aaron, the research you lead in your lab is focused on what you call intelligent interactions between a robot and its environment. Would you elaborate on that?
A lot of the useful things we want to do with robotics involve physical interaction with the world. And it turns out that contact is a really challenging problem. And so for like a legged robot, when the leg is on the ground, it can have large contact forces. But if the leg is just above the ground, it has no contact force. And so this kind of discontinuity makes it very difficult to model, to control, to learn how the system is going to work. So that's one of the things we focus on. And the other thing that comes in from these sort of challenging environments is just a large amount of uncertainty. Maybe we'll have a good model of the robot, but we're not going to have a good model of how the mud squishes or the friction on this pile of leaves. And so we need to develop methods that are robust to that kind of uncertainty.
I'd imagine that you are quite often taking your robots out of the lab and into the field to test them.
We do a lot of testing in Shenley Park right behind campus, but we've also taken our robots to deserts, to former industrial sites, to forest environments to try and sort of explore the limits of what the robots are capable of.
I was also reading about one of your robots that's bio-inspired by small mammals and can climb vertical walls. What's the overall goal?
I often say the overall goal in my lab is to make robots that can go anywhere in the world. And we will include the moon and Mars in that. And we're really sort of focused on both mobility, but then also sort of manipulation skills out in the world. And the hope is to open up access to have robots that are more capable and be able to help us in more situations. So as an example, we have a big project in the lab on environmental monitoring, sending robots out to look for contamination in soils. And depending on the site you're looking at, there may be trees, there may be rocks. We need to be able to get over these obstacles and still be able to do a site assessment and localize where contamination might be.
What excites you about robots that are bio-inspired by extinct organisms?
99% of the species that have ever lived are extinct. And so we have a much greater diversity of examples to pull from when we're looking at all of the animals that ever lived compared to just the current animals. And so we can get different examples of limbs and spine use or animals that are specialized for one kind of terrain and try and design better robots based on those insights.
The goal is to create robots that perform better in the present world. Why then look to extinct organisms? Why not focus on replicating animals that are alive and functioning today?
Just because the dinosaurs or other animals are extinct doesn't necessarily mean that they had a bad design. So the meteor comes and hits the Earth, and that's not something to do with how the design of the animal was fit or not fit for a given environment. And even if there wasn't this kind of mass extinction event, most of these species were successful for maybe 100 million years. And so we want to be able to pull from the breadth and diversity to try and understand what's possible and what works well in different environments for different tasks and different situations. For instance, on the spine, most current animals, the primary bending is sort of in the pitch direction, which would be something like a greyhound or a cheetah running, or in the yaw direction, side to side, which would be more like a lizard walk. And on the lizards, the limbs are really sprawled, while in the mammals, they're more upright. But if we look back through history, we have other combinations of limbs and spines. And we want to understand what was the environment that that animal was in, what were the tasks they were doing, to try and understand what is the value of that design aspect. And it could be something that we just don't happen to have currently in the world.
We heard from your colleague, paleontologist Dr. Asia Carter earlier. She's a postdoctoral researcher in your robotics lab, and she mentioned research you're partnering on. Looking at the gorgonopsid, an extinct saber-toothed predator that roamed the planet roughly 260 million years ago. It's a much bigger organism than the pleurocystid, which CMU researchers built a robotic replica of. What's the status of that work?
So far, we haven't sort of set up the research as we pick a dinosaur and we build the robot that matches that. Instead, we're looking at the design problem more broadly and looking at what are the range of designs we see, what are the trends, when does this design feature first occur, and what was happening in the environment when that happened, as well as things like convergence. When do we see design structures that reappear multiple times? And then from this, we want to distill down general principles. So we make a distinction. We're not trying to do biomimetics. We're not trying to exactly copy a particular species. Instead, we're trying to do bioinspiration, trying to distill down general principles for how the locomotion worked, how this design feature played into that success, and then use those principles to inspire new designs.
Okay, so a gorgonopsid-inspired robot does not exist in the world, yet. But it's my understanding you have developed other robots based on one of Asia's paleontological theories. Something to do with the spine and how we walk. Is that correct?
There's been this big explosion in legged robots. There's now a half dozen companies that will sell you a quadruped robot. The humanoid robot space is really taking off. But a lot of these robots have really stiff, rigid backs. And that's really not the way that animals are designed, either now or in the past. And so the focus has been really on spines as the key sort of design aspect that we're exploring at the moment. And what were they used for? How do they coordinate the spine and the limbs together? What type of spine? So what directions? How many degrees of freedom? What range of motion do these spines need? And so we've built a number of smaller scale quadrupeds that have different spines in them.
Any other animal anatomy, extinct or not, that you were really interested in from learning from right now?
One of the other big design challenges or design features that we've looked a lot at is tails. And this is another thing where a lot of animals use their tails dynamically. They use them for all sorts of things. We as humans don't. And very few robots have tails. And so what are we missing out on? What advantages are the animals getting from those tails that we could have in robotics?
We've been discussing animals, but what about plants? What can we learn from extinct fauna?
There's been a number of bio-inspired projects that have looked at living plants, and that extends to extinct plants. And some of the sort of characteristics you think of plants from the past are these huge, compared to what we have now, much larger structures, larger ferns, larger trees. And that can tell us stuff from sort of material design for building larger structures. Plants are really interesting in the way they sort of explore their area. You know, they move their vines around to try and catch on to the next thing to grab onto. And we usually don't see it because it's happening really slowly. And we can learn things from the way that it moves around without what seems to us like traditional intelligence of having a sensor feedback and a control loop, but it still is able to adapt and respond to the environment. So my group hasn't done anything with extinct plants specifically, but I think there's a lot of information there.
What kind of AI systems do the robots need, like computer vision and large language models, to make in-the-moment decisions about how to move? Can they then learn from their mistakes?
Absolutely. We like to talk about the mechanical intelligence. We want to design the mechanism and the dynamics of the robot to be able to get over these obstacles. And that can, in some ways, reduce the burden on the computational side. But it also opens up a lot more options. So if you have a robot that mechanically can jump over a large obstacle, do these sort of very dynamic behaviors, now that makes the planning and control and AI side much more complicated. So it's not just, I need to plan a path through this space. It's I need to decide when I'm going to jump, when I'm going to walk. Do I need to start running earlier to get up enough speed to be able to make that jump? And certainly the big challenge on that also comes from the uncertainty from the environment.
What can this bio-inspired robotics research teach us about ourselves, about human beings, and our evolution?
If we understand better how different species structure their spine, that could inform different maybe lower back prosthetics or orthoses that help prevent lower back injuries, or looking at different limb designs for that. That's not something that we're specifically looking towards, but it's certainly, if we can understand the principles for how locomotion works and how different designs are able to locomote over different kinds of terrain, then we can apply those to living systems.
Aaron, where do you see this emergent field of paleobionics in 5 to 10 years?
how do we go from what we have, which is primarily fossils, and we have scans of those fossils, and we can look at the structures. How do we go from that sort of very geometric information into some idea about behavior? Can we sort of build up a pipeline where we're taking fossils, we can scan them, recreate their kinematics, recreate their dynamics, and then understand their behavior? And can we take those tools and apply them to a robot or a model of a mechanism that's pulled straight from scans of fossils?
You've been focused on small biped robots in the lab. Have you thought of scaling that up to build robot versions of large dinosaurs to better understand how they moved and behaved? And what would be the ethical considerations?
We're nowhere near any kind of Jurassic Park situation. Instead, we're just trying to learn. So I think as engineers, it's our responsibility to think about not just how to build the robot, but also how the robot is going to be used. And so how does that affect how we might design or deploy these robots? And then also on a more societal level, like where should we be using these robots? Are the benefits of automation and robotics going to be helping everyone equally? We see these great capabilities that we're now able to make in these robotics. How do we make sure that that's benefiting everyone?
Let's bring Dr. Asia Mia Carter back into the conversation now. Asia, how far and big can this tech go in the next 5 to 10 years?
In the next 5 years, I see more autonomous paleobionic models. So something we've talked about with the soft robots is, can we make some free swimming ancient critters? There is a beautiful time period in the Earth history called the Cambrian explosion, where we have some of the most bizarre animals you'll ever see. There are animals with 6 eyes and a snout like an elephant with a claw at the end. That was a real thing, and they were swimming, right? So can we understand the transition of, from pre-Cambrian taxa, which were just kind of sea pennies on the floor, to our first free swimming ancestors? That's something I'm really excited about in the next few years, is a free swimming ancient critter.
A 6-eyed swimming elephant-like critter. Now, that would be a bizarre robot. Anything else you want to see in the next 5 years?
I am slowly rubbing my hands and asking, how big can we make a biped? Because the tallest biped is a Tyrannosaurus Rex. So, dinosaurs help us push the limit of what we think we can do, right? Can we make a human-sized biped? That's going to be a challenge in of itself. But why stop at humans, right? And if we get to a T-Rex size and we can't do it, what does that teach us about our own limitations? So I am still hoping and scheming on making a T-Rex-sized biped. Stay tuned.
And what if it escapes? Could it end up wandering around Pittsburgh?
If I have my way, yes. That is my hope.
Professor Carmel Majidi, I understand your lab collaborator and CMU mechanical engineer Professor Phil LeDuc also has dreams of building synthetic dinosaurs, though maybe not ones on the loose in the city.
If you go to the Carnegie Museum of Natural History a few years from now, or maybe a decade or two from now, you're not just going to see the bones of these extinct dinosaurs, but you'll actually see a few robot ones kind of along with them, basically resurrected and moving around.
That's a wrap for today's episode. Thanks to all my guests, and thanks to you for listening. Please check the show notes where you'll find links to additional resources for this episode. And to learn more or contact us with a story idea or comments, please visit ai.cmu.edu/podcast. If you are enjoying the show, please rate and review us on your favorite podcast site and share with friends. And be sure to subscribe so you'll never miss an episode. You've been listening to Where What If Becomes What's Next from Carnegie Mellon University, where we are exploring what AI means to industries, government, society, and you. Stay tuned and stay curious.